Yeah, thank you for the invitation. I'm really, really sorry I couldn't make it actually. It's very unfortunate. So, given the nature of the workshop, basically, I thought, I've been over the past few years. I've been working mostly on generative modeling. I've done really only a few research on Monte Carlo sampling, but yeah, given the nature of the workshop, I thought, it would be good to talk about kind of like sampling ideas. So in particular, where I will basically, in this talk, present a couple of ideas we investigated to use this kind of generative modeling idea in the context of Monte Carlo sampling. Okay. So I guess most of you in the audience are very familiar with this class of models known as denoising diffusion model. So there's a novel class of generative model that has appeared in the machine learning literature about maybe now 4 or 5 years ago, and has basically become ubiquitous in this research area. Okay. Basically, in this context, really what you're dealing with is a problem where you're given a kind of a empirical distribution, and you want to obtain new sample, basically, which looks like essentially the sample you have in your empirical distribution, but are actually not carbon copy of it. So, for example, given an empirical distribution of images, you want to generate new images actually. So this kind of model, the denoising diffusion model, have become extremely popular in generative modeling. On whether Monte Carlo sampling is a very different problem, it was tempting to see whether we could use some of the ideas which had been developed in this context in the Monte Carlo sampling framework. Okay. So one thing basically I learned by starting working on this literature is the great thing about diffusion model is somehow it's a way to learn. If I give you a stochastic process, a diffusion, it's a way to learn an approximation of the time reversal of this process. And obviously, having worked quite a lot over this kind of ideas over the past 20 years, I thought maybe indeed we could combine this kind of techniques with what I know in the sampling context, and that'll be the first part of the talk. And the second thing also that basically I've been dealing with for a very long time is that when you want to sample from a complex target distribution, a very natural strategy is to essentially instead of sampling directly for the complex target, introduce a sequence of annealed version of this target, because the annealed version of the target are much easier to sample from, and then use some kind of non-homogeneous process that basically goes smoothly toward the distribution of interest. Okay. Essentially, when you do that in denoising diffusion model, the idea is instead of annealing, you noise your target. So it's a different mechanism, but this is the very, very same high-level ideas. As we'll see, this kind of alternative to annealing has actually interesting properties. Okay. But it's also come with its own challenge, and that's what I will discuss in the second part of the talk. Okay. So to start with, I will basically kind of leverage the kind of idea of the idea of time reversing a process in the context of Monte Carlo sampling. Okay, so this is the first part of the talk. So this is a paper we wrote actually a couple of years ago, known as core-based diffusion means annealed impermanent sampling, and this is all with DeepMind colleagues actually. Okay. So this is an audience that's going to be very familiar with annealed impermanent sampling. So I'm not going to spend that much time discussing it, but here is the problem. So essentially, you're given a probability density on RD, okay, which is given in a unnormalized form. So you have access to gamma, a normalized version of pi, which you can evaluate pointwise on but you don't have access to the normalizing constant z, which is obviously the integral of gamma over the RD. Okay. And what you want to do is to come up with a mechanism so as to sample approximately from pi, and so as to estimate this normalizing constant. Okay. So what's the idea of AIS? So this is the standard idea that's been basically used everywhere in Monte Carlo. So this is what I was just mentioning 2 minutes ago. You say, okay, sampling from pi is going to be too complex, but really what I'm going to do instead is I'm going to build a path of distribution that is moving smoothly from the easy to sample distribution at the D naught pi naught to the final target distribution, pi of interest. Okay, so you build this like a smooth path of distribution. And so, for example, a very, very standard, technique is to essentially say, put the kind of pi k being proportional to the original target, original distribution, easy to sample pi naught to the power 1 minus beta, time the final target to the power beta, where beta is some kind of annealing schedule that goes from 0 to 1. Okay, so think of that if you're in the context, say in the Bayesian context, pi naught could be the prior, which is easy to sample, and gamma would be basically correspond to the likelihood, so that when you combine those terms eventually, the posterior, sorry, so that when you combine those terms, you would move from the posterior and you would gradually introduce the likelihood term so as to sample at iteration capital K from the posterior distribution of interest. So very, very standard construction. Okay, so you have this path of intermediate distribution now, goes from easy to complicated, but obviously you haven't defined a mechanism so as to sample at least approximately from them. So what's the idea really when you do annealed importance sampling? Well, is to use this kind of actually non-homogeneous Markov chain. Okay, so you start from pi naught, you initialize a non-homogeneous Markov chain from pi naught, which by construction is easy to sample, and then essentially xk is going to be sampled from some kind of transition kernel fk, where fk is typically picked as some MCMC kernel of invariant distribution pi k. But it could be something that is not exactly an MCMC kernel. It could be, for example, a EULA, unadjusted Langevin algorithm kernel. Okay, so you do that. So that define basically a distribution on path space. So the distribution of this non-homogeneous Markov chain, which is defined by this following expression. So pi naught times the product of this transition kernel. Okay. And by construction, well, you expect that if your transition kernel mix fast enough, and the sequence of the intermediate target distribution moves also slowly enough from pi naught to pi k, the final target, then the marginal distribution of xk under this non-homogeneous dynamic is roughly equal to pi. Okay, so we expect that by doing that, at least we've construct, so we have some sample at time k, which should be roughly distributed according to pi. So here, this is a simple illustration on some kind of complicated multimodal target. So we start from a Gaussian, and we move this some kind of Langevin, non-homogeneous Langevin dynamic across time, actually, on the final sample are roughly distributed according to the target. Okay, so that's nice. So that's a way at least to get some kind of sample. We shouldn't be too far from the distribution of interest, but obviously what we want to do, where we don't have access, we like to compute or estimate of the normalizing constant. We could say, okay, I have access to samples which are roughly distributed according to pi. Their marginal distribution is qk. So what I could do basically is look at this, important sampling weight, and by construction, basically the expectation of this weight should be equal to z. Okay, so that's what we like to do. But unfortunately, this important sampling estimate cannot be computed because I would like to remind you that this qk, what it is essentially the marginal distribution of xk under this complicated dynamics. Obviously, the marginal distribution doesn't admit, qk doesn't admit a closed form expression. So although we have samples which are roughly distributed according to pi, hopefully, if our proposal is good enough, we cannot use this important sampling estimate so as to obtain a non-biased estimate of the normalizing constant. Okay, so what's the idea essentially behind annealed importance sampling on its extension, in particular in the SMC sampler framework, where it's quite simple. Is you say, okay, you cannot do important sampling in the original space, but so you're going to do original important sampling on the path space. Okay, so you're going to define a target distribution on basically the space of this like a non-homogeneous sequence x0, x1, x2, xk. Okay, and the way you define it is as follow. So this is a probability distribution which by construction is going to admit at the final time step the marginal distribution pi, which is the distribution I'm interested in. And then I constructed the rest by introducing a sequence of auxiliary backward Markov transition kernel that take me so from xk to xk minus 1, the xk minus 1 to xk minus 2, and so on and so forth till basically x naught. Okay, so I have basically now, so now I'm in the context where I have a proposal distribution which is basically on the space of non-homogeneous Markov chain, which is Q. Okay, I have a target distribution which is on the same space. So essentially, I can do important sampling. Okay, if I've been careful in the way I define forward and backward. I've skipped the measure theoretic notation here to make the talk simpler. But basically, if the random decoding P of a Q is well defined, then essentially you have that the expectation of this actually extended importance rate is the expectation of this extended importance rate is given essentially by the normalizing constant of interest. Okay, so that's the really key idea that is behind annual importance sampling. Okay, so what they do in annual importance sampling is that they pick a very specific extended, basically target distribution. So what do? They say, well, okay, the way I'm going to define the extended target distribution, well, I need to define this backward Markov transition kernel. And what they pick in the annual importance sampling context is the following thing. They say, well, remember that I've assumed here so far that I move the particle forward using MCMC kernel of invariant distribution pi k at time k. And basically, I use this actually backward Markov transition kernel to define my extended target. Okay, and you can convince yourself that this thing is indeed a Markov kernel because if you sum that over xk, basically you have to sum this numerator over xk, and because fk plus 1 is invariant with respect to pi k plus 1, basically this thing is equal to pi k plus 1 sk plus 1, which cancel with this term. Okay, so this is a backward Markov transition kernel. This thing is nice because, you know, when you plug that into the expression of your extended importance weight, which is, remember, is this gamma unnormalized extended target distribution of a Q, where the expression of the log weight is very, very simple and is given by this expression here. Okay, so it's very, very kind of simple expression. And this is really annual importance sampling, also known as Jarzynski-Crookes identity in physics. Okay, so everybody, I think most people in the audience are very familiar with this kind of scheme. Okay, but now see, this is something which is actually somehow nice, but not optimal, as you can convince yourself easily. So first, imagine that you have transition kernel that makes extremely fast. Okay, that is essentially so fast that after one application of the transition kernel fk, your sample are actually admit a marginal distribution which is exactly equal to pi k. So you mix, it's instantaneous mixing, essentially, it's perfect. Then when you see that really you end up with some kind of the variance of the log importance weight is strictly positive, actually. That's not very satisfactory. Whereas if you could compute this kind of marginal importance weight, the one that relies on, you know, not having this, you know, extension, extended auxiliary target distribution, but would just require the knowledge of the marginal distribution of x capital K under the forward dynamic, then the variance of your importance weight would be zero. Okay, so that shows that already is something a bit fishy there. And now another thing that maybe is perhaps actually even more I think traumatic about annual importance sampling is the following point. So we say, okay, you know, so as to obtain a sample approximately at time k from pi, we run this non-homogeneous Markov chain, you know, starting from pi naught, pi, and then we try to move from pi 1, pi 2, pi 1, and so forth. But you could say, well, okay, you know, assume that pi naught, you know, is actually already not too far from pi. Why would you bother actually defining the sequence of intermediate distribution, you would pick pi 1, pi 2, pi capital K equal to pi, basically, and you would like to apply the annealing impermanent sampling in this context. Okay, it seems to be natural that there's no reason why you should bother doing annealing. You say you're already quite close to pi. Pi node is already quite close to pi, and say pi as a simple geometry, say log concave. Well, if you do that, then you have this remarkable thing that obviously, if you mix very well and you run your homogeneous Markov chain Monte Carlo algorithm for many iterations, then well, you're gonna have QK, which is really very close to pi, but the AIS importance weight is basically gamma x naught of pi naught x naught. Okay, so it tells you all the work you did after sampling x naught from pi naught is being forgotten by your annealing impermanent sampling algorithm, which is actually kind of problematic. And you see that it tells you already there's something a bit wrong going on here actually with this choice of actually backward Markov transition kernel. Okay, so here I give you another illustration of a simple toy example where we can compute essentially the exact marginal distribution, because we are dealing with simple Gaussian target distribution with Gibbs sampling on annealed impermanent sampling. And we see, so this is here the RMSE in terms of actually the log weight minus the log normalizing constant, which is known exactly in our case. And we see that basically it is much higher for this kind of AIS mechanism than it is obviously for the algorithm that could use actually the marginal distribution. Okay, so that's all nice, but obviously it's not really practical because, again, for complicated problem, you will not be able to compute the marginal distribution of the final state of your Markov chain. Okay, so still we're going to try to make progress on that and try to identify at least what is the kind of optimal choice of backward Markov transition kernel we should be using so as to reduce the variance of my essentially extended impermanent sampling estimate of Z. Okay, so this is all result. I think it's first appeared in a paper with Delmar in 2006, but it's good to remember the result. So this result is the following. It tells you, okay, you have basically a proposal Q, which is this kind of given by the distribution with non-homogeneous Markov chain. You need to define an extended target, okay, P, and you want to do it so as that basically this extended target is such that the variance of actually the evidence estimate, normalizing constant estimate, that is the variance of the impedance weight on the extended space, is minimized. Okay, and if you do that, it's a simple calculation to show that really what you should pick an extended target distribution, which is such that its final time marginal is basically pi of xk, on essentially this kind of backward Markov transition kernel, they are defined by the time reversal of the forward dynamic. Okay, so here you notice that contrary to AIS, I don't use pi k plus 1 at the top and at the numerator and the denominator. Here what it is the marginal distribution of xk under the forward dynamic at time k and at time k plus 1. And this thing is also obviously a Markov kernel. Okay? And it's a simple thing to prove. You can prove it just using the law of total variance. You can also do this kind of same thing using the KL decomposition. It's actually fairly trivial. Okay. And in particular, what this thing tells you is that if you were able to pick this choice of backward Markov transition kernel, and we see this is problematic because it depends on this kind of marginal distribution of this non-homogeneous Markov chain, and it's typically not tractable. But if you were able to pick that, then essentially the evidence estimate, your importance weight estimate of the normalizing constant, which simply boils down to the intractable, actually marginal impermanent sampling estimate I couldn't compute in the first place. Okay, so seems we haven't made much progress, but at least we identify really that if we wanted to have actually a low variance estimate of the normalizing constant what we should do we should try to pick this backward Markov transition that essentially are approximating the time reversal of the forward process. Okay, so that's actually quite interesting. To summarize, the key result of this slide is that the optimal extended target distribution you basically should pick is the time reversal of Q, the forward dynamic, but which is initialized at the target distribution pi instead of Q capital K. That's what it is. Okay, so that's an interesting result. Unfortunately, except in very, very simple case, it's very unclear how to approximate that until, well, actually it was very unclear until 2-3 years ago, okay, where essentially this idea of denoising diffusions algorithm came across. Okay, so now we've done everything in discrete time to start with, but now let's move a bit to continuous time and try to see essentially what it corresponds to forward dynamic on this kind of time reversal initialized at pi. Okay. I'm telling you the following thing now. So I'm going to consider a process, a stochastic process, which is going to be, so it's going to be a continuous time version of annealed impermanent sampling. And this process is simply a non-homogeneous Langevin dynamic, which essentially target pi t at time t. Okay? And so you would run that long enough somehow so that the marginal distribution of xt at time, of xt on this forward dynamic is roughly distributed according to pi. Okay? And now, really, what we want to do, what we need is to define further our impermanent sampling estimate. We need to approximate its the time reversal of this diffusion, but the time of the reversal of the diffusion initialized at pi. Okay, so this is what I've written. So it turned out the time reversal of the diffusion is a diffusion. This is a diffusion which basically depends on the term which is so known as the score. So this is the gradient with respect to x of log of essentially the intractable marginal density of x under the forward dynamic. So somehow, at least we can write somehow fairly explicitly what is the time reversal of this, the time reversal we need to approximate for the case of a non-homogeneous Langevin dynamic. Okay, and we can do exactly the same thing for underdamped Langevin. It's in the paper if you're interested. Okay, so nice, everything, and we can write those expressions, but it doesn't tell us yet how to approximate this intractable so-called score. So this is the Stein score and not the Fisher score. So basically what we're going to do something which is a very machine learning type thing. So we say, okay, I need to approximate this time reversal here. I don't have access to it. So what do I do? Where I'm going to basically replace the intractable term by some kind of parametric approximation. So it's going to be a neural net typically. And so as to essentially learn the parameter theta of this neural net, where we're going to try to minimize a kind of discrepancy measure between essentially the distribution induced, the path measure induced by this approximate diffusion on this actually target diffusion. So if you do that, we use the Kullback-Leibler. So if you look at the Kullback-Leibler divergence between those two, the two distribution on path space, well, it turns out that basically it's equivalent to minimize the expectation of the integral over time of the square difference between my parametric approximation of the score on the score. Okay, but that's not really useful because we don't have access to the intractable score to start with. So it's not that I can even evaluate unbiasedly this objective or its gradient. So I cannot really do much with that. But by somehow some simple standard rearrangement, which are in the literature in machine learning are known as kind of denoising for matching, it turns out you can rewrite essentially this criterion as follow. Okay, so you're going to partition essentially the time interval into K subinterval, capital K subinterval, and you introduce essentially the gradient of the log of the transition of this non-homogeneous Markov chain. Okay, so you don't have access exactly to this expression for complicated diffusion, but basically you make an approximation of that, and that gives you a criterion that you can minimize using your favorite, stochastic optimization algorithm, so as to learn an approximation of the score, and so that is an approximation of the time reversal of the diffusion initialized at pi. Okay. And once you've got that, then essentially you're able to compute an approximate. You're able to compute the impermanence weight in extended space using this approximate time reversal. And if the approximation was to be exact, it would boil down to the marginal impermanence sampling estimate, which we know is the best thing we can do. Okay. So I spare you the thing. Obviously, in practice, it's all done in discrete time, and there's some argument to justify why it's all correct. Okay, and I give you here some kind of example where we compare essentially this kind of standard annealed impermanence sampling with this estimate where we actually learn is the extended target distribution we need to so as to compute the unbiased estimate of the normalizing constant. And we see that it gains you can get quite significant benefit in terms of when we use it to train some kind of variational autoencoder and for some simple target distribution. Okay, so that's a kind of interesting. Whether for most application you would care about that, I think it's actually kind of doubtful. It's really when you're in a scenario quite classical in machine learning where you're doing some kind of variational inference, amortized variational inference, in which case I think it makes sense. In the more general context, the fact that you're going to spend quite a bit of time training the parameter of your neural net is actually too consuming for most applications. But still, I'm happy to answer question later on. Okay. So that's the first application of this kind of denoising diffusion idea to Monte Carlo sampling. And this is somehow for me one way to complete this long line of work I had started 20 years ago, which was like basically, when we had an SMC sampler, identifying was the optimal, the time reversal, the optimal extended target distribution we should put in, and so on and so forth. Okay, so that's the first part of the talk. And the second part of the talk is something which is somehow closer to what people have been doing in generative modeling. This is a paper that appeared last year at iClear. It's also with people, Will Gratwall from DeepMind and Francisco Fargas, who at the time was an intern at DeepMind and is finishing his PhD in Cambridge right now. Okay, so in this case, we're going to do something. I'm going to present the idea. So the idea is the following. Okay, so if you look at what we've done in the previous talk, essentially we were fixing the proposal. Okay, that is we were fixing the proposal. This was the distribution Q that was defined by a non-homogeneous Markov chain. And we were learning some kind of the time reversal of this proposal to reweight or sample efficiently to compute the normalizing constant of pi. Okay, so but you see, by doing this, we haven't done anything at the problem. So if the proposal was bad, the previous method, what he was doing was not improving anything because we were not modifying the proposal. We were just actually modifying the way we reweight the sample from the proposal. So here we're going to do something actually quite different. So we're going to do something which is the scenario where we're going to fix the kind of extended target distribution. And we're going to essentially, this time we fix the target distribution, extended target distribution on path space, and we're going to approximate the optimal proposal based on this extended target distribution. So first talk, previous part of my talk, I was fixing the proposal and trying to learn an extended target to reweight my sample efficiently. Now I do the different thing, the the reverse thing where I fix the extended target distribution and I try to approximate the best proposal to target this extended target distribution. So it's really related to things that have been done for control SMC, the path integral sampler, and so on and so forth. Okay, so how does it work? So here you go. So I'm going to define an extended target distribution as follows. So this is a process defined by diffusion. So you start X naught from pi, and you diffuse for Arnstein-Reinbeck process. Okay? And somehow you're going to diffuse long enough that basically the marginal distribution of X capital T is roughly Gaussian. Okay? So that's the extended target distribution. It's a virtual process. I cannot sample from it because sampling from this extended target distribution will require actually being able to sample from the target pi, which is my goal. Okay, but I can still write it. Okay, and I'm telling you, well, okay, so that's good. So this is my extended target distribution. So what I want to do, so as to sample from it, what could I do? Well, maybe the best thing to do would sample from the time reversal of this process. So this process, it goes from pi and it diffuses slowly towards a multivariate normal distribution. Now, if I want to do Monte Carlo sampling, I like to do the reverse. That is somehow starting from the multivariate Gaussian distribution and basically reverse this kind of noising dynamic of the Arnstein-Reinbeck process and go basically till sample from the original target pi. Okay, so that's the idea, the key idea behind the noising diffusion model, but you can apply exactly the same idea in Monte Carlo methods. Okay, so I'm telling you simply, if we could simulate the time reversal of this process, which is given by this diffusion, then we would obtain at time capital T a sample from pi. Okay, but there's a problem with that because essentially we don't have access to the score of basically of the forward dynamics. So what is PT here? This is the marginal distribution of XT under the forward distribution. Okay, so to be able to compute basically this, to implement this time reversal, really what we would need to do, we need to approximate this score. Okay, so what we can do, where we can do basically something which is very similar to what we were doing in the previous talk, and this is the standard thing done in machine learning. That is, again, you can replace the score by some kind of parametric approximation, typical some kind of neural net. Try to learn the parameter of this neural net by minimizing a suitable probability divergence, and then by simulating for this approximation of the time reversal, you are going to have an approximate sample from pi. Okay. For this type of result, because this thing is very, very similar to what has been done in generative modeling, it's actually exactly the same idea. Then you have quite a few theoretical results that have been presented in the literature. In particular, here I quote some results of Shinoshui that were presented in 2022. So if you could approximate the score, that'd be amazing. Okay. Now the key thing is obviously, are you going to approximate this score again? We're going to term it's not easy. Okay. So first thing, I'm just going to skip that first. You could say, okay, what I could do is basically try to use this kind of technique that was presented in the previous talk. This was like minimizing this kind of like denoising score matching type criterion. Okay, so you could try to do that. So unfortunately, you cannot. Okay, so this is a bit of math. You could try to use this kind of KL here. Okay, so if you minimize the Kullback level of discrepancy between the distribution of my approximate time reversal and the true time reversal, it admits this simple expression here. Okay, that's very nice. And if you remember, in the previous part of the talk, I had this intractable term actually that was appearing, and I could get rid of it by using a simple trick. Okay, and could replace the intractable score by the score of the log transition of my noising diffusion, of my diffusion. It turns out, in this context, I cannot do that. I cannot do that because my expectation is not on the P, it's on the Q theta. So this trick doesn't work. So that's not the way you can actually learn the parameter of your neural net approximation of the score, because this criterion is actually useless. So you need to play a bit with this expression, and it turned out actually you can rewrite the curl between the path measure induced by your approximate time reversal or the true time reversal using some kind of a few elementary manipulation, which lead you to a tractable actually criterion. So I'm going to skip you that. Essentially, you end up having to minimize some kind of expectation, which is of this form, an expectation with respect to the distribution, the distribution you approximate time reversal. So everything here can be estimated biasly. The gradient can be estimated biasly. So once again, you can learn the score, an approximation to the score. And once you learn the approximation to the score, you simulate from your approximate time reversal, and that gives you an approximate sample from pi. Okay. So that's actually a kind of nice approach. Only for those of you, it's actually nothing but some kind of variational inference, but variational inference that is conducted by introducing a variational distribution, which is essentially the marginal distribution of the diffusion process. So that's why it's actually fairly flexible. Okay, so that's one thing you can do. But there's other thing you could be doing, which I'm perhaps not going to mention. I'm going to mention briefly because I think still it's interesting. Is the following thing. Okay, so at the high level idea, what do you have? You have some sample x, say from pi. Okay, so you have x which is distributed according to pi, and you add essentially some noise to it. Okay, I put an Einstein-Bay process, but think of just putting a Brownian motion, and you could do exactly the same type of thing. Okay, so think of that as some kind of Gaussian noise. Okay, and really, I'm telling you that if you want to do sampling, really the only thing you need to be able to do really is to be able to compute the score that is the gradient of the log of the marginal distribution of this sample. Okay, that's the only thing you need to do. If you were able to do that, then somehow you'd be done, because you could plug that in your time reversal, and that's done. Okay, so what is basically this expression, the gradient of the score of y, where there's two things that basically the standard identity that is in the literature, which is known as 3D identity or denoising score identity. Okay, so this expression is given. It tells you that really the gradient of log of py, the score of y, is nothing but the gradient of the log of the noise density, which is typically going to be Gaussian, so you can evaluate that. But this is you need to compute the expectation of that with respect to the conditional distribution of x given y. Okay. So what can you do when you do that? Well, in machine learning, people they tend to favor this identity because you see they have access to sample of x as well and sample of y. So essentially, they estimate this conditional expectation for regression. In the context we are in, you know that x is distributed according to pi, but you don't have access basically to sample from it. So you cannot use regression to basically estimate this conditional expectation. But what you can do simply, you can do something that people cannot do in generative modeling, is you could also try to approximate this conditional distribution. So you could tell me, oh, that's a little bit crazy, because essentially you had this original problem of sampling from pi, and now you're telling me, well, you replace that by having to sampling from some kind of conditional distribution of basically x from pi, given some kind of noisy version of pi, of x, okay? Well, it turns out there are scenarios where this thing is going to be very well behaved and always look concave, so actually you're in business, okay? So it's possible to do something good with that. Another thing we can do as well, you can use another score identity, and it's useful in particular at low noise level, because somehow you can also write the score of y as basically the score of x, also integrated with respect to px given y. Okay, so essentially this identity can be leveraged. You can use MCMC so as to approximate the score, or approximate message passing to come up with alternatives. You don't like neural network, you can try to estimate that through local Monte Carlo and then plug that into your time reversal. So there's another way to approximate this time reversal. You don't have to use necessarily this kind of machine learning type ideas. I can talk more about it if you have any question later on. Okay, so I'm not discussing that, but you should keep in mind that all these things are feasible as well. Okay, so this thing already works, so we play with that. So first of all, I should say that when I started this project, I was not a believer at all. I was sure that SMC would really essentially do much better than any of these techniques, which is somehow kind of simple variational technique, where you kind of parameterize the distribution through the marginal as a marginal diffusion process, and you have a neural net approximation of the score. Is things that I would not have basically believed in, about 5 years ago. But it turned out that this thing actually empirically works quite well. It's kind of remarkably well, actually, given this was done in a kind of short 3-month project. It's actually quite competitive to SMC. Okay, so it's actually quite kind of interesting that using this kind of simple idea, you manage to get technique that do actually quite well. Okay, so overall, you can leverage this idea of denoising diffusion for sampling as well. For the last part of the talk, essentially that gives you a new kind of new variational inference technique, so as to sample from pi to approximate pi and ever estimate this normalizing constant. So it's competitive to SMC. When we did it, it was still computationally more expensive actually than SMC, because you have to do the training, which is expensive. But turned out that I think there's actually a lot of things that we've realized and we could speed it up. But I'm not saying it's better than SMC, but it's really competitive and it's a completely different approach. We tried many variations actually at the time when we were looking at this project, and none of them actually proved very useful. But again, I think there's much more to explore at basically on this topic. On now with a bit more understanding what's going on, I think we could improve those techniques. Okay, that's all. Thank you.